Hi everybody and welcome to the Mangano Digital Academy, the house of digital dentistry. In this short lecture I will talk about the accuracy in full arch digital implant impression, and in particular I will focus my attention on the topic of the scan body. That is very important because when we talk about digital implant impression we talk about several things. We need to consider several factors. First, the intraoral scanner, of course, because each intraoral scanner has an intrinsic accuracy and an intrinsic error. Then the operator, because the operator is very important with different skill, different level of experience and different strategies that are more suitable or less suitable for that machine. Then the patient, because the number of implants is quite relevant and the inclination and the depth of the implant are also relevant factor. The environmental condition are also relevant. The amount of light, the source of lights and the temperature. But the scan body, it's really key. And sometimes we forget about it because we usually consider the implant transfer in analog impressions just like simple transfer of the position of the implant. And we don't look at them so carefully. But when we talk about the scan body, there are more implications. There are more things that we need to understand deeply in order to reduce the final error of our impression in order to obtain a high quality digital implant impression. And these topics, we need to revise a little bit this topic during the lecture, are the design of the scan body, the material the scan body is made, the tolerance during the fabrication in particular, because I will show you the results of one study in which I have investigated exactly this topic, and then the torque, the position, if the position is correct or not, because if you torque it too much or less, the position may be mistaken. So all these aspects are very important. And finally, the congruence between the correspondence between the mesh and the library file. And this congruence also depends by the scan body, because it depends also by the tolerance of the scan body. It depends, of course, by the intraoral scanner as well. It depends by many factors. But let's focus our attention on the scan body. So the implant scan body, because it's something new in our field, and we need to understand it very well. And I've read a lot in the literature recently, in particular the paper of Mizumoto and colleague, very beautiful paper. And I see that there are some factors that we need to consider when we talk about implant scan bodies. First, the structure. The scan bodies are divided into three parts. Basically, we have a base, that is the mating part with the implant or the implant analog. Then we have the body. The body, it's a cylinder usually, and then the scan region, that is usually a flat surface of an intaglio, a slide on the top of the body. So that is an index that adds to the superimposition inside a computer-assisted design software of the library over the mesh. So these are the three most important components of the scan body, and these can be made in different materials, in PIC entirely. So in this case we will talk about a one-piece PIC scan body, or in metal, in titanium or in titanium alloys, and in this case we can have a one-piece titanium or titanium alloy scan body, but they can also be two pieces, like the base in metal and the body and the scan region in PIC. Why? Because of course if we have two materials we can take the benefit from both, and we will see it. The benefit to have a metal part engaging in a metal connection, for example, particularly in the case of conical connection, and also the benefit of the optical properties of the polyether ether ketone. The design, of course, is important. The tolerance in the fabrication is key, and it is exactly the aspect that we are going to investigate in this lecture. And the position, I've seen some paper dealing with the torque of insertion of the scan body. It's also very important. So let's revise the structure of the scan body. As I told you, there's a base, there's a body, and there's a scan region. The base is the mating part, the most apical part, the part that is inserted inside the implant or the implant analog. The body is the body of the cylinder, and then we have the scan region, this flat region or intaglio that is an index and help during the superimposition. So we have this solution. On the left you can see a one-piece PIC scan body from the sternum. On the right you can see a two-piece scan body, metal on the base and polyether ether ketone on the body and on the scan region. Let's talk about the base a little bit. Let me say that the base is responsible for creating a mating surface between implant and scan body, and can be metal or PIC, but I prefer in metal because, of course, metal versus metal is much better than metal versus PIC. So, considering that the implant is in metal, the connection of the implant is in metal, if we use a scan body with a PIC base, we need to consider that probably there will be a distortion of the PIC base, and we cannot use it too many times. Probably it should be considered a disposable scan body, the one-piece scan body in PIC, and not exactly suitable for conical connection. In fact, in this case, Straumann produced this one-piece scan body for flat-to-flat connection, internal hexagon or sometimes external hexagon, and so it's very important to consider it. But at the same time, yes, metal probably is the best solution for the base, but because we can use it more time and it's not subject to distortion and is not suffering from process of decontamination like sterilization. But we need to consider that anyway, for the PIC it's even worse, but for the metal too, there's a problem for conical connection. We can have some issues in the zeta axis, so for the height of the scan body, because it's very difficult to produce perfect conical connection, and even a little mistake along this connection can determine a mismatch on the zeta axis, so problems with the height of the scan body, and it's important. So let me say that PIC base should be handled with care. It's a disposable, and we can use it one time and no more, ideally, and definitely they are not indicated for conical connection. Metal bases are much more better. We should use them, but at the same time they suffer, particularly for conical connection. Exclusively, I would say, for conical connection we have this problem. If deeply tapered, we can have a displacement in zeta, even with the metal base. With the PIC base it can be even worse. So it is important to remember this, because later in the study we will see that the results with the conical connection are not so good in height. In terms of height we have more tolerances, but it is natural, it's normal, it's not something surprising. Let's go to the body. The body can be in PIC, the body can be in metal. There are also one-piece metal scan body. Generally, usually it is in PIC because of the optical properties. Polyether ether ketone has better optical properties. It helps the scan body to make it work, to reconstruct the surface perfectly. Of course, if there are two pieces with the body in PIC and the mating part, the base in metal, they need to be assembled by the company. They cannot be disassembled by the operator, because in the latter case we can have a lot of troubles and it's not appropriate. I mean, we can have big mistakes in the position of the implant at the end. So the best thing is to have a compromise between the optical properties, better to choose the PIC, but the machinability, because you need to understand that PIC is a very difficult material to machine and to work on it, because there are changes in the temperature while preparing it, and there can be distortion, there can be contraction. So it's quite more tricky to work on the polyether ether ketone, to mill and to turn polyether ether ketone, than to work on the metals. For this reason, some producers, they decided to use scan bodies entirely in metal, and it's an interesting choice, particularly if they are sandblasted, but only a few companies do this. Most of the companies use two-piece scan body assembled by the company, and they work quite well anyway. The scan region. Let's talk about the scan region a little bit. The scan region is on the top of the cylinder usually, and it's an intaglio, it's an index, it's something that, yes, helps the superimposition, so helps the dental technician, and most of all the superimposition algorithm inside the 3Shape software, the exocad software, the dental wing software, to make the superimposition between of the library file over the mesh that we captured with our intraoral scanner, but it must be considered that this surface should not be too wide. I mean, technically it should be less than 20% of the whole surface of the cylinder, because otherwise there's a risk of attraction. I mean, this flat surface can act as the only player in the game and can attract too much. The mesh can attract too much, the mesh flat surface can attract too much the library file. And so there can be a mismatch in the position of the implant. So it's very important, this area, because you need to drive all the process, but at the same time the process must be controlled through the diameter and the height of the cylinder, of the scan body. I would say that in the past the companies produced scan bodies with complex shapes, forms, angles, but these kind of shapes are not appropriate. But it's better to have smooth surfaces, ideally a cylinder, and easy surface to reproduce for the scan body, for the scanner. The scan body doesn't need to be complex. The design should be as simple as possible. There are a lot of studies actually in the current literature dealing with the scan bodies and how the geometry of the scan body can affect the final accuracy of the impression. Usually this aspect is investigated together with different scan strategies. So there's a little bit of confusion because there are so many factors together. The most important thing is to keep in mind this, and all dental technicians should control these steps all the time after the superimposition of the library over the mesh of the scan body. They should control through a visual inspection the colorimetric map, and ideally each single superimposition should result in less than 10 micron error, particularly if we deal with a full arch. If you are making a full arch in a fully edentulous patient with 6 or 8 scan bodies, it's quite important, because a congruence in these steps allow us to obtain very good results and an excellent passive fit later of the structure, of the replica first and then the structure later. But a lack of congruence, if we have an error above 50 micron per each scan body, then we cannot have adequate passive fitting, we cannot have adequate absence of marginal gap. We have troubles, and generally, usually the structure doesn't sit properly. So it is very important. And it depends by the scan body, this congruence, because as you can imagine, if the scan body is fabricated not very well, there's an error in the fabrication. We buy the scan body, we don't see this error, we don't see this mistake, but at the end, these mistakes create an issue in the final result. So the workflow is affected by this issue. So we wanted to investigate, as a research group, what is the fabrication tolerance of implant scan bodies. And we investigated it in this study that we have submitted to the International Journal of Prosthodontics recently, together with Dr. Henriette Lerner, Dr. Fabrizia Luongo, Dr. Giuseppe Luongo. We compared basically 6 different scan bodies that we bought from, because they are commercially available in the market, and we investigated them. We investigated them with an optical microscope and then with a precision probing, through precision probing, and then we compared the results of each single specimen with the reference file. The reference files we obtained through the analysis and the evaluation and the measurements made on the library file provided by the manufacturer. So these were the 6 scan bodies that we evaluated, 2 from Nobel Biocare, 2 from Straumann, 1 from BTK, and 1 from Megagen. As you can see, they are very different each other. The first one from Nobel is a flat-to-flat connection, an external hexagon. Then we have a conical connection from Nobel Biocare. Then we have 2 flat-to-flat connection, one-piece PIC scan bodies for the Straumann bone level and Straumann tissue level, and then we conclude with 2 implants with conical connection, 2 pieces scan body in PIC and with a metal base. So usually all scan body are made according to this concept, the 2 piece. We wanted to investigate if this different design and different material may have an effect on the tolerances also. This is the whole set of samples. Of course, we bought several pieces per type, so at the end we investigated 30 pieces in all, so 5 per type, for 5 per 630. And the study was based on 3 steps. First, we measured the library files as reference. We collected this data, we put in one table, then we investigated with optical microscopy and through precision probing with a Renishaw probe machine. We investigated each single physical sample. We gathered all this data and we compared this data to the reference data in order to have an idea of the tolerances during the fabrication of the scan bodies. So the first phase, it was very easy. We simply evaluated using a software the dimension, diameter, 8, and also this plane, this intaglio, this slide on the top, the scan region. We evaluated how the libraries files of the different scan body were made, like Nobel Biocare Brannemar, Nobel Biocare conical connection with the different characteristics, Straumann bone level 4.1 mm diameter, Straumann tissue level 4.8 mm diameter with all the characteristics. We annotate them in a table. Biotech BTK-KR with the characteristic once again, and the Megagen NRH. The Megagen NRH doesn't have the intaglio, the slide on the surface, so we evaluated another thing. As you can see, we evaluated and we measured on the top this measure, and we considered it the reference for the plane, even if we don't have a plane here. And this is what we found related to the libraries, so the computer-assisted design evaluation of the library files. These are our references. Now we have to test our sample, our physical pieces, our specimens, with the volumetric analysis of the scan bodies. And this volumetric analysis was performed by optical microscopy plus precision probing. So each single piece, each single scan body underwent this examination. And this is an example of what we did with the microscope. It was a QI smart scope flash 200, 33 pair, and then a Renishaw for the probing machine was a Renishaw R0.25 with a calibration tolerance of 0.0013 mm. This is the Nobel Biocare hexagonal connection, as you can see. This is the conical connection. So we gathered some video, we collected some video of all the aspects of this evaluation. Each single scan body required to set the machine on purpose with a program in order to calibrate the machine exactly on that type of implant analog. The implant analog was blocked inside the machine, and then we could proceed with the evaluation through physical probing, and it took a lot of time because we gathered a lot of measure, a lot of sample from the same 5 scan bodies per group. So either it is the Nobel Biocare conical connection, as we can see. Here we have a Straumann bone level evaluation. Once again, we see the video, and first of all, the calibration of the machine when talking about the probing, and then after the machine has been calibrated, after the system is being set for that specific implant system, for that specific implant analog and implant scan bodies, then we could proceed with the assessment of the scan body itself. Same consideration for the Straumann tissue level. Of course, we have the whole set of video and the whole material captured during the process. Once again, calibration, before the calibration, after blocking the implant analog inside. I want to point out that all the scan body was screwed and positioned according to the manufacturer recommendation, using the proper torque and everything, even if some manufacturers don't have a specific recommendation, but it's also very important because the position is key, as well as the manufacturing tolerance. These were the BTK scan bodies, a 2-piece scan body with the body and in peak with the scan region that has an angle, and the base in metal, and it's a conical connection, so it's quite more difficult to prepare them properly in terms of 8, and we will see it in the results. And finally, we evaluated the mega scan body. In this case, we choose the 13 millimeter ones, even if there are also available 9 millimeter scan bodies. The company has also specific scan healing abutments, but in this case, we decided to evaluate exactly this kind of scan bodies that are very easy to use for fixed implant prosthodontics. So once again, in this case, an evaluation of these specimens repeated for the whole specimen per group, and then we have these results. These are the descriptive statistic, means plus standard deviation, and as we can see, there are tolerances. So these pieces physically are not identical to the library, and we did expect it, but how much they differ? Let's go to the analysis of the tolerances. Tolerances in 8 measurement. As expected, we see that the results for conical connection is not so good like for the flat-to-flat connection. The only surprising result for me is the very excellent results with the Nobel Biocare conical connection. These scan bodies made for Nobel Biocare by ELOS, and they made it very well. Of course, the Straumann scan body performed very well because they were flat-to-flat connection. It is expected, and they were also one piece, not assembled, so they have an advantage in terms of 8 measurement. As we can see graphically, we see the differences between the different scan bodies, and in this table we can see the difference in 8 measurements. So on the top and right of the table we see the differences, and on the bottom and on the left we see the p-values, and if the p-values is less than 0.05, there's a statistically significant difference between group of scan bodies. But once again, if we measure 8, so if we make our measurement in the zeta axis, of course we understand that conical connection are more prone to error. It's not a disaster because of course we believe that conical connection implants, they have big advantage clinically, and so we need to consider this aspect clinical. Let's go to tolerance in diameter measurement. Let me say that it's the most important thing because the cylinder plays the most important role, and the diameter of the cylinder plays the most important role when superimposing the library file on the mesh. Here we have very little mistakes. For example, for MegaGen, we have a mean difference of 2 microns. It's very little. I mean, it's something that it's negligible. I mean, we have high precision material, and the results are more or less similar for the whole scan body. So it means that also the polyether ketone is worked quite well by the Straumann company. The ELOS scan bodies also performed very well. So we have very good and consistent results. And as we can see from this graph, we see that the diameter the tolerances in diameter are very limited because we can see that we are below 10 microns of tolerance most of the time, and in some cases, like for the MegaGen, we are only a few microns, 2-3 microns also of mistakes. So basically we are talking about high quality products, and the tolerance is very limited for diameter, and it's very important because the diameter plays a major role in the superimposition process. In this table we see the differences in diameter measurement. Once again, on the top and right of the table, the distances, the differences, and on the left bottom of the table, the p-values. P-values reveal a statistically significant difference when we have a value that is less than 0.05. So once again, we see that there are statistically significant differences in some cases between the machine, but I would say that rarely for the diameter, much more in the other measurement, in height measurement and in plane measurement. Let's watch the last aspect, the tolerances in plane measurement. In this case, we have, yes, differences between the different scan bodies. Particularly, we have a very good performance for the Straumann tissue level. And I would say that there are distances, of course, between the different pieces, and also the repeatability is not so high like in the previous measurement, but anyway we have more or less some stable results for the most of the scan bodies. For the MegaGen, it was not possible to calculate the plane measurement because we didn't have a plane, but anyway we calculated the distance and the differences between the two different points of the top of the scan body, and as you can see, the result was very good also in this case. With regard to differences in plane measurement, once again we have this table. On the top and right we see the differences between a couple of different type of scan bodies, and on the bottom and the left of the table we see that the p-values with in evidence the statistically significant differences between the different couple of groups. And in conclusion, what are the conclusions of this study? First of all, we have tolerances in the production of the different scan bodies. So even if they are limited, even if the manufacturer provides us very good solution and very good pieces and with low tolerances exist, and we found them among the different scan bodies. And we found also statistically significant differences in the tolerance between different type of scan body produced by different companies. So both in height and diameter and plane measurement, we found differences among the different scan bodies. It is crucial, therefore, to underline that the company needs to reduce this manufacturing tolerance, these fabrication tolerances, because this fabrication tolerance can affect negatively, they can contribute to inaccuracy of the final restoration, because they affect the final implant position. So in order to transfer the implant position predictably, we need to reduce the fabrication tolerance of different scan bodies, and it is very important. Also in zeta, but also in diameter and in plane measurement. It is key. Let me invite you to visit the website of the Mangano Digital Academy, the House of Digital Dentistry. We love different software and different tools here, and we cooperate with we use different machines. You can follow us in the YouTube, in Facebook, Instagram, and Twitter. And thank you very much for your attention.